Hello everyone, I'm Junjie Ye from Tongji University. Today I'm honored to present our work, DarkLighter, Light Up the Darkness for UV Tracking. As the title says, we target facilitating nighttime UV tracking in this work. For audiences who are not familiar with visual tracking, let me read a quick introduction. Given an initial position of an object, that is, a bounding box describes its location and scale. Tracking approaches are supposed to estimate the position of the tracked object in the following frames. Visual object tracking is a fundamental task in many UAV-related applications. For example, target following, autonomous landing, and so on. Motivated by biological neural networks, tracking approaches based on convolutional neural network are constructed to track objects like human eyes. In this manner, tracking approaches, those trained with numerous data, achieve satisfying performance. Due to multifarious tracking-related tasks, UAVs inevitably work at night. We have collected a nighttime UV tracking benchmark in our previous work. Here are some first frames of the dataset. Objects in these scenarios are hard to distinguish by human eyes. So how is the performance of SOTA trackers at these scenarios? Here goes some qualitative results. One can say that the top-ranked trackers can hardly maintain their satisfying tracking performance at night. There are two possible reasons to the failures. On the one hand, the training data are generally captured under favorable light conditions. In this case, the learned models are just like a person that never experienced the nighttime. On the other hand, images captured at night are always with high-level noise, low contrast, and low brightness. In extreme low light conditions where naked eyes can't see clearly, no wonder CNNs lose their effectiveness in extracting features. So how can we carry trackers into darkness? A promising solution is to conduct low light enhancement prior to visual tracking. In order to be implemented in UAV applications, we provide some standards that such a low-light enhancer must meet. Take the limited computing resources and complex working conditions of UAVs into consideration. Such an enhancer must be lightweight, robust, easy to deploy, and most importantly, beneficial to object tracking. Nevertheless, previous works in low-light enhancement generally focus on improving visual quality of dark images. Low-light enhancement for high-level tasks, for instance, object tracking, is not investigated well. According to the Retenix theory, an observed image can be decomposed into reflectance and illumination maps. Take noise into consideration. A noise map is added into the Retenix model. The reflectance can be regarded as the wavelength of the light reflected by the object. Since the reflectance is determined by the properties of the object, it is supposed to remain constant. Hence, reflectance can be regarded as the object's true color. Naturally thinking, tracking the object with its true color, regardless of the light conditions, may lead to a more robust performance. Hence, we tend to design a Retenix-inspired enhancer. Rewriting the Retenix model, we can get this formulation. So the question is how to estimate L and N. Previous Retenix-based low-light enhancers generally obtain illumination layer and noise layer in a one-shot way. In our consideration, there are numerous scenarios and low light conditions in practice. The direction projection between a low-light image and its illumination layer and noise layer can be extremely complex. It may be hard to learn a model that can simulate such a projection relationship. In the IROS2021, an iterative curve projection model is proposed to enlighten low-light images progressively, inspired by which we propose an iterative Retinix model in this work. As the figure shows, DarkLighter dedicates to peel-off illumination and noise maps iteratively. Given a low-light image is 0, DarkLighter erases illumination and noise progressively. After a total of I iterations, the illumination and noise maps are relatively cleaned up, and the final output, Si, is regarded as the reflectance R of the image. Therefore, we need to estimate the noise map and the illumination map in every iteration. We train a map estimation network, that is, the MENet, to estimate image-specific illumination and noise maps. Specifically, MENet consists of 7 convolutional layers, as shown in the figure. Taking the initial low-light image as input, after passing through several convolutional layers, a set of illumination maps and noise maps are obtained for iterative decomposition. To enable MENet with robust maps estimation ability, several consumption functions are designed to guide the training process. DarkLighter towards lighting up the template patch and the search patches, since the tracked object is centered at the template patch and generally appears in the central area of the search patches. It is worth paying more attention to enhance the central area. In this loss, the enhanced image is divided into P non-overlapping patches. The average intensity value Y of each patch is regularized to approximate a well illumination value I, L, and W is the weight matrix to emphasize the central area. The illumination regularization loss is added to constrain the smoothness of each illumination component. The noise estimation loss is tended to restrain the overall intensity of noise maps. As for the color intensity loss, it bridges 3 channels and constrains their intensity to a relatively same level. Moreover, since the semantic information of images plays a pivotal role in object tracking, the degradation of semantic information is enhanced images can be easily lead to tracking failure. To this end, the semantic fidelity loss is introduced, which constrains the difference between enhanced and the original images. Finally, as the figure shows, DarkLighter serves as a pre-processing step prior to tracking approaches. The low-light images are lighted up before being fed into the backbone. Here goes a visual comparison of features extracted from the original and the enhanced images. It can be seen clearly that features extracted from the enhanced patch are more salient and discriminable compared to those from the original patch. In the experiments, we first implement DarkLighter on 4 different trackers, including DIM50, PRDIM50, SAM, APN, and SAM RPN++. The evaluation is conducted on the UAV Dark 135 benchmark. The rainbow plots illustrated the performance of trackers, where the trackers with DarkLighter enabled are highlighted with bold font in the legend. The performance gains of DarkLighter bring to trackers are also reported in the table. One can say that DarkLighter boosts nighttime tracking performance favorably, specifically with an increase of more than 29% in success rate and 21% in precision. DarkLighter upgrades the dark tracking ability of SAM APN significantly. Afterward, we compare the DarkLighter and other general low-light enhancement approaches to testify the advantages of DarkLighter in boosting nighttime tracking. Superinely, though Enlightened GAN improves the video quality of images indeed, it causes the degradation of tracking performance slightly. We conjecture that video quality cannot guarantee satisfactory tracking accuracy. As for zero DCE and LIN, they elevate the tracking performance to a certain extent. Designed for robust dark tracking, DarkLighter allows tracking accuracy further. As for the ablation study, we investigate the contribution of different loss functions. Tracking performance of baseline under the effects of DarkLighter with different combinations of losses is illustrated in the figure. The results show that all loss functions in DarkLighter are pivotal and contribute to the facilitating of tracking performance. Further, we test DarkLighter on an NVIDIA Jetson AGX server. It runs a high speed of over 100 frames per second, which is sufficient for computing resource-limited UAVs. Finally, here goes some demo videos to give a comparison of trackers with and without DarkLighter. To sum up, DarkLighter is a lightweight low-light enhancer. It runs a high speed of over 100 frames per second on an embedded system. It's toward facilitating nighttime tracking, and it serves as a plug-and-play manner. However, I must say DarkLighter does have drawbacks. It lacks close cooperation with tracking approaches and is designed in an intuitive way. Hence, we believe there still remains a huge room to boost nighttime UAV tracking. Our code is available on this page. And here goes our laboratory's homepage and my personal webpage. Feel free to visit our most recent works. Contact me without hesitation if you find any questions or if you want a discussion. My contact information can be found on my personal webpage. That's all of my presentations. Thank you for your listening.